Hey guys, today we will be doing a video on A-level physics P5 paper. So basically another past paper walkthrough, and the past paper we will be dealing with is October-November 2015 P53. So I suggest that you get either printouts of this paper or you open this up in another tab. And I will again remind you in the beginning that you have a total of 1 hour 15 minutes for this paper. So organization of your time effectively is a key skill required, along with the ability to plan, analyze and evaluate data and draw conclusions. So let's begin. A beaker contains water and some metal blocks as shown in figure 1.1. So we basically have a beaker that contains water, and within that water we have immersed some metal blocks. Two of them are visible in the diagram, right? Metal block 1, metal block 2 immersed in water, and we have a heater immersed as well. And a student uses an electrical heater to produce a particular temperature increase in the water. Alright? And so basically it is suggested that the electrical energy E supplied to the heater to basically cause that particular temperature rise is related to the mass m of metal blocks by the relationship E is equal to am plus b, and this m is probably the mass of all the metal blocks as it appears from the question statement. And E is basically P into T. That is the power that was of the heater multiplied by the time that the heater was working. Alright. E in this scenario may also be somewhat related to MC delta theta. Could have some sort of a relationship with it, although obviously that is not the equation we are given, because MC delta theta would have to do with the temperature rise of the metal blocks as opposed to the temperature rise in the water, both of which would likely have different values. So if we were actually talking about E, we would have two parts to MC and delta theta, one for the water and the other for the metal blocks, because we have two different things that are part of the environment and both of them have different values of C and therefore would have different temperature rises for the same amount of energy provided over a period of time. So what I do is I often just write this equation out somewhere and try to have a brief analysis of it before reading any further. So we know that E is the energy we are supplying, or we need to supply for a particular temperature rise. Alright, that is a constant in each scenario. No matter how many metal blocks we have, we still need a particular temperature rise. Alright, so m could be the value on the x-axis, and therefore the independent variable, and E would therefore be the dependent variable, because we'd have to measure the value of E needed to bring about the particular constant temperature change for varying values of m. This is x, this is y. A would likely be the gradient of the whatever graph, straight line graph we have, and B would be the y-intercept. And we could basically have constant temperature rise or something, or constant power, right? So we have to design a laboratory experiment to test the relationship between A and M, obviously, and explain how results could draw out values for A and B. And you have to be able to draw a diagram showing the arrangement of your equipment, and in your account you ought to pay attention to procedure, measurements to be taken, variable control, data analysis, and safety precautions. So we have 15 marks. The first 2 marks, how to get them? You identify the variables. Independent variable is the one you would be changing, and that would be the value of M. And how would you change that? You'd basically increase the number of metal blocks that are in the water containing beaker, and you'd have to measure out the mass of each metal block that you will be adding using a electronic balance, for example. And the dependent variable would be the amount of energy needed to bring about that particular temperature rise. Obviously there would be some correlation. And how do you know the value of the energy? This heater would have to be connected to a particular EMF supply. Alright. And you'd have to provide a constant voltage and electricity to the heater. So you basically need a constant a EMF supply which is providing constant power to the heater. And what is the formula of power? Is basically V into I, and so you need a value of the voltage over the heater, and you can simply connect a voltmeter like this in parallel, and you also need an ammeter, and P is equal to VI would be the power. And you may have a rheostat over here with which you can vary the amount of current and the voltage drop, so in order that you may keep the power constant in some case that there is some variation with the initial power supply. Alright. And how do you collect E is equal to purity? We basically measure the amount of time needed for the temperature change, and we'd have a thermometer over here, and we'd have a stopwatch. Remember, you have to completely draw out this circuit. Have a thermometer and have a stopwatch and have a mass balance. You need to have a complete practical setup, as if you are giving out the instruction to a complete newbie who has no idea how to carry everything out, and you have to tell him everything, every safety precaution, because he might mess things up badly. And so you put the thermometer in, and then you turn on the heater. You know the value of the P, and you the moment you turn on the heater, you turn on the stopwatch, and you observe the time taken for the thermometer to register the temperature rise we want. And that moment we simply stop the stopwatch and note down the time interval needed for that change to happen. Now we have the value of time, and energy is basically power into time. So you need to write out all those important formulas as well. So we have given the procedure to be followed, the measurements to be taken, and any other thing that should be there. As for the thermometer, you should have something that is is pretty precise, pretty accurate, something with 0.1 to 0.2 degrees Celsius graduations, that would work. And what sort of variables ought you keep constant? The amount of water. The volume of water definitely needs to be constant. Alright? And you shouldn't, and the metal block, the material of the metal block should similarly be the constant. So if initially we're placing copper block of a particular purity, when you choose to increase the mass by adding another metal block of whatever value of M, it needs to be of copper of similar purity. Get it? And anything else? It would likely be a good idea that the surrounding temperature is the same, because we don't want it to be varying the temperature of the water. And if in this entire setup could be insulated, that would be a good idea. And a safety precaution could be you shouldn't be touching the heater, obviously, and or the heated beaker or the water. You'd get burnt. Not a good idea. So we have a basic outline of the 15 marks that we need, and now we need a more, like, I want to tell you how to actually write all of this down. And then there is the analysis of the data part. So this equation basically mirrors y is equal to mx plus c. So a would be equivalent to the gradient and b would be equivalent to the y-intercept, and if we get a straight line with a positive gradient, then we know this relationship is valid, right? So let's go about actually telling how to do this. Number one, in the diagram portion, which accounts for almost 2 marks, you'd draw the speaker, and you'd draw the metal block, and you'd draw the heater. And what else would you do? You will have to complete the circuitry. You will have to connect a voltmeter like this between these two, so it is in parallel, and you need, or even better, you could simply do this. Complete it like this. You could have a voltmeter between these 2 points. You could have an A meter over here. You could have a rheostat over here, and you could have a constant power voltage supply over here. And and obviously you need a thermometer over here, and it wouldn't be hanging in the air. It would need to have been connected to something. You could have a retort stand, and you can basically show a mass balance somewhere over there, and a stopwatch. Again, don't make it seem overhanging, make it seem like it's placed somewhere over there. And you need to have it labeled at least 2 of the things you added. So you may label the thermometer as thermometer with 0.1 degrees Celsius divisions, and you may also label the A meter, the voltmeter, and the constant power voltage supply. You may even label the rheostat, but I believe only 2 labels are considered necessary, right? So you have basically drawn out what you will in the diagram portion. Next over here you write independent variable, the value of M, dependent variable, the value of E, and the controlled variable could be the volume of water, the surrounding temperature. Alright. And what is the procedure to be followed? You vary the value of m by adding or removing metal blocks from the container. Alright, and you use a electronic balance to measure the mass of any metal block you are to be adding, right? And the metal blocks all have to be of the same metal and the same purity. For example, they all have to be either made up of iron of a particular purity or say aluminum of a particular purity. And when you're adding or removing the metal blocks, care must be taken that you don't remove a lot of the water that might mess up your results. Also, probably because the water might be a bit heated up, you have to use some sort of an instrument to put the metal block in and never your hands. That seems like a bad idea. That's how you're varying the value of m. Right? So we want a particular rise in the temperature of water each time, and to register said increase we need a thermometer hanging vertically with its bulb immersed completely, and basically it is clamped to a retort stand. Alright, and for example the temperature rise may be of 5 degrees Celsius, may be of something of a bigger value, right? So we have that thermometer dipped in and we want a particular rise in the temperature, so you need note the initial value of the temperature. Alright, and as you know, you have the heater dipped in and you know how to calculate the value of the P. The value of the P is obviously constant, but just in case you want to calculate it some other way, right? Or the first time you want to calculate the value of P, you have a stopwatch. The moment you start the heater, you click it on and you closely observe the thermometer until it reaches that point in which the final temp minus the initial temp would equate the delta theta you want, and then you close the stopwatch and you know the value of the time interval. And then what do? You need to know the value of the power, which is basically V into I, and for that you take the value of V from the voltmeter, which is in parallel to the heater, and the ammeter that is in series with the heater. And you ought to be observing that the values of I and V are constant. They ought to be, right? And to calculate E, you basically E is equal to P into T. So now the measurements to be taken would obviously be voltage from voltmeter, value of current in amperes from the ammeter, value of time corresponding to a particular temperature rise from the stopwatch, value of m for the metal blocks from a electronic balance, and analysis of the data. You basically know that E is the y and m is the x, and therefore A would be the gradient and B would be the y-intercept, because this is a reflection of the straight line equation y is equal to mx plus c, and B is the y-intercept and A is the gradient. Safety precaution: do not touch the beaker barehanded. It is pretty hot, you might get burned. Same goes for the heater as well, or the water in it. Let's just see what they have to say about this. MS 53. Right, just give me a moment. Sort the mark scheme. So defining the problem accounts for 3 marks. M is the independent variable and E is the dependent variable. And we have to keep the temperature change of water constant. Yep. And we have to keep the mass or the volume of the water constant. You ought to be getting 3 marks for this, easy peasy. Labeled diagram including labeled thermometer with bulb in water and at least one other label. A workable circuit to determine E should include power supply, heater and ammeter and voltmeter. Yep. Method to determine change in temperature, initial temp, final temp and subtract. Yep. Use of balance to measure the mass of blocks. Something I missed out, you shouldn't have still water so that metal is in thermal equilibrium. So you would have 3, 4, 5, 6, 7 marks from this, and you just need 8 more, and there's a lot of things you can get those from. Plot a graph of E against M. A would be the gradient and B would be the y-intercept. 9. Precaution linked to hot heater water. Example, use gloves or use tongs. This is a name I forgot. Tongs are basically the instrument you use for like taking stuff. So this is 10 marks. Let's not give this mark, just leave it 9 because I did forget the name. Relevant points might include method to ensure that EMF of the power supply is constant, variable power supply, variable resistor, and yep, 10. Keep the starting temperature constant. That was implied but not really stated. Again, implied but not stated. Add insulation to sides, 11. Use of timer in equation, 12. This wasn't mentioned. 13. So we have successfully gotten 13 marks. Next time we hopefully get the 2 marks remaining, but this is more than enough. So what was it that we actually missed out? You know, something I've noticed that when doing these questions, you often note things and you don't really remember all of them when you're doing some other paper. And what I do is I keep a diary in which I write down stuff or this sort of stuff I may have forgotten, and then I observe patterns and I don't really forget the things I noted. So get a diary, write W15, question paper 53, question 1. So what did we miss out? Equalization, temperature equalization, and this should be enough of a hint to understand what it is that you meant. See? Method to ensure that EMF of the power supply is constant. So basically you just write all the things you missed out. I'd write stirring water for the sake of achieving thermal equilibrium, and I'd write tongs because then I might remember the name and what it was linked with. I'd write use of large temperature change, for example, to reduce percentage uncertainty, because I always forget this particular point about reducing percentage uncertainty. See, and this really works out for me, leads to improvement, a lot of it. Another thing when you're doing this paper is take an examiner report because they're important, and most people actually don't really pay that much attention to it. But as for me, I think I can learn a lot from merely reading about the stuff other people did wrong or the examiners noted were done wrong by a lot of people. So no evidence of time constraint. Majority scripts were clearly written and graph were well drawn with points. Alright. Practical course, yep, this is important. If you don't have any actual hands-on experience, you might be a bit lacking, and so it's always a good idea to get some. The candidates were required to design a lab experiment to investigate how the electrical energy, capital E, supplied to a heater in water for a particular temperature change varied with the mass m of metal blocks in the water, right? Candidates were also required to And candidates were also required to verify the given equation and explain how the constants A and B could be determined from the measurements. And in general, the description of the experiment by candidates has improved, which is a good thing. And a bad thing, because probably the marking would be more difficult. A significant number of candidates did not read the question carefully, so answered in terms of specific heat capacity of the metal, which wasn't really mentioned anywhere. Something you should have noticed and kept to yourself. Some weaker candidates stated that they would change the energy to the system and measure the corresponding change in mass, which is a bit sucky. For those of you who have read the nuclear topic, may actually have made sense, except that those small changes could not possibly have been measured with a lab balance. Most candidates could identify independent and dependent variables, and a significant number stated that the mass of the water needed to be kept constant. Many candidates did not state that the change in temperature of the water needed to be kept constant. And a significant number wrote control instead of constant for the constant variable, and this is not awarded credit. Again, something to note. And credit was available for a clearly labeled diagram and circuit. Not just a diagram, the circuit as well. Diagrams should be realistic, has nothing hanging in thin air, well labeled, and have correct workable electrical circuit. Should include necessary pieces of equipment set up as they would in an actual experiment, a labeled thermometer with a bulb in the water. Some candidates did not include appropriate measuring instruments to enable the power energy of the heater to be calculated, and by that I mean a voltmeter and an ammeter. A common mistake was to include a variable resistor in the circuit with a voltmeter placed to measure the PD of both heater and variable resistor, which is sucky because we want the voltage of the variable resistor, not the variable resistor, we just want it of the heater, just of the heater. But there would obviously be some voltage drop across the variable resistor, and that is the point. Determining the change in temperature requires measurement by thermometer of the initial and the final temperature and subtraction of the values, and very few candidates obtained credit for stating this. Yay, if you had written this, you would have, like I would have, which is really great to think about. Almost all candidates obtained credit for describing an appropriate instrument to determine the mass of the metal blocks. A few candidates confused mass and weight. Don't do that. Credit was available for data analysis. Choose appropriate axis. Graph of E is AM plus B is not acceptable. You aren't telling us anything with this. Some candidates gained credit for suggesting a graph of M against E. To gain further credit, needed to indicate how the constants A and B could be determined from the graph. And a significant number stated a straight line through the origin, not through the origin. Obviously, there's going to be a y-intercept because it is AM plus B, and B is obviously the y-intercept, and B is most likely not 0. And candidates should be encouraged to give clearly reasoned safety precautions that are relevant to the experiment. To a safety precaution relating to the use of a relevant safety item, for example, a glove, a tongue, and the reason for its use, touching, carrying a hot named piece of apparatus. Including appropriate detail, answers suggested they did not have sufficient practical experience. Yeah, you should, and you should get that. Vague responses were not credited. Always be specific in your explanation. Yep. And this is it for this video. Next video I will be doing the question number 2 of this paper, which has to do with a lot with uncertainties and graphical evaluation and other stuff. Hopefully you'll find this and the other one very helpful. If you like, please like, subscribe, and comment. Constructive criticism is always welcome, and I'm always ready to have some sort of improvements to improve my work, to improve my videos. Thank you.